But yeah, I have other people that definitely
Like
are more patient.
Yeah, I'm not liking this one.
That would
Okay.
be interested. I'll ask them about it and I'll like, oh, is it working now?
I'm opening a different stream.
Yeah, so I'll say, yeah, I'll let you know.
Alright, yeah.
All right.
What is this? Okay. So it should be fine. Certain, because I also just told everyone not to. Yeah, so far. Well, my family's here, my old roommate's here.
So have you met Professor Wei Chen in person or no?
I don't think formally, no.
Yeah, nice to meet you here. Yes, yeah. Thanks for inviting me. Yeah. So we're going to just, there's no table here, right?
Yeah.
No, formal is.
So is your student, women good help with anything or? Yeah.
Yeah, you
No one's in this one.
So actually it's not. Actually it's.
Oh,
Yeah, there's no button to start this one. It's kind of remarkably confusing. Huh? Yeah. Hang on. Oh, Professor Ward. Professor Voides, hello.
yeah, so I will try to send stuff.
Yeah. I don't know if you saw that there's food outside around the corner.
Okay.
Yeah, if you wanted coffee or anything like that.
Sure. No, this is fine. I'll definitely have to share. If I did share, this would be very difficult to. We're learning a lot about this.
Oh. Huh? That's not mine. I don't know whose luggage that is. Actually.
If you want to send me the link for the
Yeah, let me. You mean this one or the other one?
either.
I'll send you this one.
Tell me to check this Scribble.
Yeah, let me email it to you. Does this one go to your phone? Hey, Shu. How's it going? That works. Thanks, Raymond.
Oh,
Thanks for that point.
Yes.
yeah, that's okay.
The one that you sent.
Yeah, I don't know, maybe the other.
Did you meet my dad?
Like I just found out the computer and I didn't know. I didn't know that. I have two, actually, almost 3-year-old, but almost 1-year-old. Is it too late?
Oh, I don't know if they give you my coffee, but there's coffee like around the corner.
Oh, okay.
There is?
Yeah, there's a bunch of food coffee.
Thank you. No, I appreciate that.
I didn't think I heard about it. I'm very happy to be here.
We need coffee.
Hey, Richard.
Hey, good luck.
Very nice. Daniela, you know me. That's not great. Well, Daniela doesn't have any questions.
You see your screen, I think there's something
What was the election link?
Yeah.
Were you able to click on the link in the chat?
Yeah.
Okay.
That won't work.
You guys
Yeah,
see
I-
this row? I'm gonna sit the on yours. These are kind of small. There's no list of this.
Get on it, like,
Free to say wherever.
I'm not as good.
Don't say wherever. Thank you. Should be fine. Just want to get to that cake. I want to get to that cake.
Yeah, me too.
Yeah, Jay said she was able to get on.
there's a bypass link.
Yeah.
It's easy to find.
The actual scheduled link didn't work, so I had to set up like a backup.
So there's still people out there, so we'll
Okay, yeah. I know these always start a few minutes late. Oh, what should I do afterwards about the food? Should we go back?
You can just put it
Yeah.
somebody.
Yeah, you can.
So maybe I should go get a cart.
It's very likely that it may be gone by the time this is over, because I'm in the lunch area, so people may just decide to
Oh, you take the sign.
Okay.
Yeah, yeah. That's
that way people can. Definitely got to.
yeah, I wasn't sure if I should just go straight to the office. Or I should get this stuff somehow, or go to my office and get the cart and not get this stuff.
We might be able to.
We can probably, there's a bunch of us, I think.
I don't want to keep waiting around for the private part.
Yeah.
Well, you can,
Sometimes it's fast.
we can probably just,
Yeah.
we can probably just take it away during your.
Yes.
Oh, okay. Yeah, I don't think I've seen it much.
We usually just see the back.
Yeah. It's more like there's people outside. No, I don't think anyone in particular. I'm not sure. There's some people tuning into the live stream. Paywen said he would be late, most likely, because he's catching an Uber from Argonne. But he was a while ago. He was doing that, so maybe like 10 or 20 minutes late.
I'm so excited.
Yeah.
You get the cheaper one, it's like 90%. You just have less.
Okay. I'm glad I got a room with a good projector.
What's that?
I'm glad I got a room with a good projector.
You have a pointer?
Yeah, yeah.
Chris is like red green colorblind.
It'll be. Oh no, this plot might. Wait, this plot should be an orange and blue. If it is, I'll have to point.
Okay, so we'll get started, and I'm going to introduce Nick. So welcome to his Thesis Defense. For those of you who have not attended a Thesis Defense before, we have sort of an open public talk by the candidate, and then afterwards we'll take questions and answers from the audience, and then there'll be a closed-door session where the committee, which is sitting over here, gets to ask Nick as many questions as they want, and he has to defend his research work, and then after that we'll have the results. And so that's the plan for the presentation. Nick joined my group in 2014. He's actually the first Northwestern student to join my group, so he was quite pivotal in getting the group running here at Northwestern as I transferred from Drexel here to Northwestern. He's done a number of things. He actually came to Northwestern with 2 research publications in the group. He's published 4 articles already. He has 2 additional ones, I guess, planned. One was just appeared today.
Yeah.
In Physics like 5 minutes ago. So he's been quite productive in terms of research. He's given back. He likes to do outreach activities. He's taught middle school kids how to program, I guess, in Python.
Yeah.
And while here doing the PhD work, for which he'll tell you a little bit about, he won't tell you everything, otherwise we'll be here all day. He also had 2 internships. So he went to Los Alamos for 1 summer and then had an internship at Google as well. And so for the next 40 minutes or so, we'll hear about Nick's work in the area of data science for design of functional materials.
Thank you, James. Okay, so first, I'd like to just start off with explaining what are functional materials for people who maybe aren't familiar with the terminology. Essentially, materials that are defined by their inherent properties. Often, this is to distinguish them from, say, like structural materials, which are incorporated basically into larger macrostructures. But it usually entails things like electronics and energy with different properties that are primarily a focus here. So in electronics and magnetism, optics all for, say, information processing, sensors as well for, say, smart devices or things that are intelligently built into the environment. And of course, as material scientists, we're interested in finding new functional materials with properties that are of relevance to technological applications. Unfortunately, this problem is very difficult, hence why our department employs so many grad students. One of the things about functional materials that's sort of inherent to them is that they're often sensitive to very small changes that lead to drastic swings in properties. So for instance, a small amount of doping might totally change material from a semiconductor to sort of a metallically conducting compound. Or small strains, for instance, might induce large effects. There's a wide design space, so you have this huge array of naturally occurring elements in the periodic table, of which you can combine into, say, compounds with multiple elements in them in varying stoichiometries. Identifying a priori which composition and which structure or which arrangement of those compositions is going to give you ideal properties is not necessarily easy to know ahead of time. And we can't just sort of high throughput go through and do all the experiments and test everything, because to do so is a very expensive task. We don't have a lot of, say, robotics that could carry out tens of thousands or hundreds of thousands of experiments easily at the fidelity that we require to actually do materials discovery. So we'd like to find some other way, perhaps, of exploring this sort of design space and finding new materials. One such avenue to do that is computationally. And you can do that in one mechanism using solid-state physical simulations or from density functional theory. I'm not going to go into the details of density functional theory, but you can essentially think of it as you input, say, a composition in its atomic arrangement, its crystal structure, into a computer. You do some numerical processing, solving an analog to the Schrodinger equation. Then a few hours later, depending on how many atoms you have, you get the energy of that structure out, which can then be used to compute, and the wave functions which can be used to compute properties relevant to the electronic structure, like the density of states, the forces on the atoms, which relate to the mechanical properties, say the formation energy of that compound, whether it's going to be stable relative to some other possible structure or composition. You get phonons, so computing things like the electron interaction with the lattice for, say, trying to do predictions of electronic properties, and say magnetic moments, if you're interested in discovering whether this material has some interesting magnetism, magnetic ordering, or something like that. In this vein, I actually did an example case study here that I'll talk about using DFT, examining the difference between one commonly sort of studied material, these cubic perovskites, which have an atomic arrangement with these metal O6 octahedra here with A-site alkaline earth cations. An example prototypical chemistry would be barium titanate. And I'm going to be contrasting that with these hexagonally face stacked chains of compounds. So they're not as commonly observed, actually. By Pauling's rules, these are relatively rare structures to be found in nature. An example composition would be barium manganite, but barium nickelite also has this. And as a result of the sort of rarity, they're not as well studied. And we wanted to know whether the sort of structure that's unique to these compounds might be of interest for, say, tailoring the electronic properties or other properties of these materials. So one thing that's unique about these structures is that you can sort of have gradients of the amount of phase sharing. So you can have this prototypical normal perovskite, cubic perovskite example, you have only corner sharing between the octahedra. Whereas you can have also the end member, you can have full phase sharing, but you can also have sort of gradations that you can think of as like a knob for tuning properties potentially, depending on the structure here. Intermediates of say 50% phase sharing or 33% phase sharing. And one of the interesting things about say this arrangement where you're stacking chains of MO6 octahedra on their faces is that unlike in the traditional cubic perovskites where you have, say, the triply degenerate T2G energy levels on the bottom here, you actually have a further splitting between an A1G sort of orbital pointing along these chains and then EG pi orbitals, which are pointing sort of to the faces of this octahedra. So you have an additional sort of complexity in the physical properties of the system that you don't get in these typical cubic perovskites. And then you also have your sort of traditional EG sigma high energy orbitals as well. One thing that I'm going to point out here is that this will come up later, this eta parameter. It's the ratio of this sort of in-plane bond length to this out-of-plane, or this sort of along the chain bond length. And that's going to be, I'll come up later, as a metric of how much this distortion that leads to the splitting of these orbitals is in the structure. And I'll show how that's a sort of relevant parameter for engineering properties. So one of the first things I'd like to talk about is just a basic, as you change the percent phase sharing of this structure, or these polymorphs, looking at two prototypical compositions, barium titanate, which is also known to have, say, both cubic corner sharing structures as well as a phase sharing analog at high pressure, what the effect is on the electronic band gap of this material, so the energy required to excite an electron from the valence band to the conduction band. And we can actually see for barium manganite, there's changes on the order of several hundred millieV going from the sort of cubic corner connected structure up to this phase sharing analog. The barium titanate is kind of an interesting example because its end members are both polar, which sort of affects the band gap differently from the structures in the middle, which are nonpolar. But essentially, the band gap stays pretty much flat, as you might expect for like a G0 system that's not affected. And another interesting thing is we looked at the elastic properties of these materials. So you might expect that as you're switching from corner connected to face connected chains, that you might expect some sort of stiffness along the chains relative to, say, a case where the octahedra are allowed to rotate around the corners. But actually, we observed that while these, if you look at these from left to right, these first two are in plane sort of elastic constants, and the third one is out of plane. So while the along the chain is indeed the strongest direction. Overall, the elastic constants all soften, and you actually observe a very sharp decrease in bulk modulus. And again, the sort of cusp is due to polar structures being softer than nonpolar structures. So we can actually see that this parameter that we can sort of think about tuning potentially through different synthesis techniques gives us another knob for engineering the properties in these materials. But that's not the only interesting thing. One of the things I mentioned earlier is this eta parameter. So this trigonal distortion, which is defined as sort of changing the ratio of these lengths to be not equal to 1. In the normal octahedral, they're 1. You could think about the effect of this on, say, the band structure. So this distortion gives rise to these, in the real material, gives rise to these bonding and anti-bonding A1G orbitals, which are oriented along the chains here. You can visualize the sort of partial charge densities on the bottom here to the bonding and anti-bonding ones. And they lead correspondingly to a split sort of in these bands in the conduction band. And the interesting thing is that as you compress the chains further together, as eta essentially gets much larger than 1, this energy goes further and further down, this energy goes further and further up, but the end result is that your band gap is being shrunk as you do this. So you can actually see, and this effect is most pronounced in D0 titanates because the bottom of the conduction band in this case is the A1G is the lowest in energy, so in the barium manganite, because they're D3, they already have the band gap is not between A1G and other states, or A1G and the oxygen P states, but other metal states. So the effect there is much smaller. But here for barium titanate, you can see these dashed lines represent the sort of zero strain case or unstrained case. As you go from these neighboring eta values, you're changing the band gap by almost in the order of half an EV, which is quite sizable. And I should mention again that there is sort of an analog in rhombohedral perovskites, which are a known low temperature phase of, say, barium titanate, but the effect is much weaker there, and it's more difficult to control that distortion there. So just to conclude from this section, these trigonal distortions unique to phase-sharing polymorphs can achieve band gap changes in hundreds of MeV and D0 titanates, which is kind of interesting phenomena. I would say overall, the bond topology changing of these compositions is something that is really underexplored. In fact, when it has been explored, it's often been as, say, a competing polymorph for, say, ion conduction in solid oxide fuel cells. So actually, it's been viewed as a detriment historically. But there's so many compositions that might potentially be amenable to be found in these polymorphs with advanced synthesis techniques. I think they're kind of worth looking into. And there are additional properties that I didn't have time to get into as much here, but potentially having, say, multiple cations stacked along those chains, you could think about creating interesting magnetic orders that you might not find in the normal perovskite variants, which would be interesting to see. Okay, so that was an example of using, I want to say traditional density functional theory, even though density functional theory as a field has only been around for a few decades. But there's still some problems even using computation to analyze materials for functional materials design. So there's less of, say, experimental bottleneck in terms of moving atoms around, but you still have to use experts, so either a grad student or professor or postdocs, and their time is very expensive and they don't have a lot of it. So we are looking for a way that's, say, faster. Some properties, for instance, you either have to measure, you have to go out and measure because they're too computationally expensive to study. So for instance, LDA and GGA, which are some of the most commonly used DFT exchange correlation functionals, have reasonable scaling costs. And if you know computer science, big O notation, these are n cube scaling. So as you increase the number of electrons, your computational cost grows by to the power 3. So in practice, that means even for relatively accurate simulations, not even super accurate ones, you're talking about maybe hundreds of atoms at most, up to 1,000. So you can't simulate things like, say, disordered glasses or large structures like grain boundaries or things like that that require larger simulation sizes. And the other thing is that normal traditional computational DFT is often viewed as computational experiments, but you're not necessarily leveraging all the information from the past other studies on related materials, for instance. You're more or less starting anew with each calculation. It would be nice if there was some way to take materials that are, say, similar in some sense and use information from them to make your life easier in calculating new things, or maybe to show you what the trends are you should expect. And that's where I would say data science, which is sort of a new emerging field can come in handy. Often when people, maybe not too much these days because people are more savvy, but in the older days, people would think of maybe something like this when they heard the word data science, some guy in a suit touching holograms or some kind of black magic. I think of data science more like this, where it's sort of holistic, encompassing of a bunch of different aspects related to programming, related to data processing, collection, and structuring, and then also visualization, but also good old-fashioned just having expertise in the sort of area that you're working in, background knowledge, intuition. And then there's also the element of algorithms, which is the machine learning part that everyone assumes is all of data science, but is really just one component. I'm going to talk about how we use data science to study one really interesting phenomena that I find really cool, which is these metal insulator transitions. So metal insulator transitions are pretty, there's a few dozen of them, but they're relatively uncommon in nature. And the interesting thing is that with some sort of critical parameter, say temperature or doping, you have this huge switch in resistivity from, say, something that's almost as conductive as copper all the way down to something that's essentially a rock or insulator. And it'd be really interesting if we could find new materials with these transitions that had changes in log resistivity that were very high, so that had really great on-off ratios, but also occurred at temperatures that were close to the sort of ambient human experience, or some other temperature that's high where we might want to have an operating electronic system. They're predominantly found in transition metal oxides due to sort of some of the physics I'll mention later. But they are unfortunately sort of limited in our current applications today to some niche fields. But it'd be nice if we could figure out how to find more of them. So one materials family that does exhibit this transition are these rare earth nickelates. So you have some rare earth cation going from lutetium all the way to, say, neodymium or praseodymium, nickel, then O3. So these are perovskite analogs, like the structure I mentioned earlier, the corner sharing ones, not the phase sharing ones. And they have these interesting phase diagram where they go from an orthorhombic sort of paramagnetic metallic state through a metal insulator transition, so into this purple region. And then they are at the same time going through a structural transition to a monoclinic phase, and also at even lower temperature, they go to a antiferromagnetic ordering at very low temperature. Interestingly, for neodymium or praseodymium, the metal insulator transition and the magnetic ordering transition are at the same temperature. And it would be nice, you could see here that these temperatures go from 600 Kelvin. So for people who aren't scientists, 300 Kelvin is about room temperature. So you would like to have these temperatures either be adjustable, either be closer to room temperature or to be further up, depending on whatever application you're interested in. But to do that, we sort of have to understand what's the physical mechanism of the transition. And unfortunately, that's sort of under debate as to which mechanism between charge ordering or bond disproportionation is this Jahn-Teller effect. And I'll show in the next slide what those distortions actually look like. I should mention here this tolerance factor here is related to the size of the rare earth cation. So as you go from left to right, the size of the rare earth cation is getting larger. And essentially what you would expect is that due to sort of packing arguments, as you go from left to right, the structure should overall become less sort of tilted and rotated, less disordered, and more like a straight cubic perovskite. And that will have important implications for the strength of this ordering temperature, or the magnitude of it. So that phase diagram is one way to visualize sort of this family of materials, but another way you can think about visualizing them is in terms of distortion modes, symmetry adapted distortion modes. So as the structure goes from, say, a hypothetical high symmetry cubic phase down to orthorhombic or monoclinic phase, there are a set of symmetry allowed cooperative displacements of the atoms that can be quantified using group theory and assigned labels. And you could think of that as another sort of quantitative way, instead of just the tolerance factor, to quantify the distortions of these materials. And two of the distortions that I'll highlight here are related to physical mechanisms that I just mentioned. So this A-type Jahn-Teller is related to the Jahn-Teller mechanism possibly mentioned earlier, where along the sort of apical bond lengths, you have an alternating lengthening and shortening, and then you have the reverse in the end plane, lengthening and shortening. And that leads to another splitting of the EG orbitals in this material, which could lead to a sudden inability to conduct electrons. So that's one possible mechanism that physically makes sense. Another mechanism that is potentially occurring is this octahedral weaving, which is related to charge ordering. So the smaller octahedra, this is exaggerated by the way, would be nickel sites where you have, say, a higher oxidation state than on the purple site. So on average, you might have, say, nickel D7, but on one site it might functionally order into D6, another site it might order into D8. And that could also lead to a sudden inability to conduct electrons due to the charge ordering here. And different people have proposed different sort of experimental confirmation of one theory or the other. And I was interested in whether you could actually see whether the magnitudes of these eigen distortions of these mode decompositions could give you some kind of insight into which physical mechanism is occurring. So the most simple thing you could think of doing is plotting the correlation between, say, a given mode and some ordering, temperature of ordering. So this is the magnetic ordering temperature, and this is the metal insulator transition. And so a purple square indicates a high degree of positive correlation. A dark orange indicates a high degree of negative correlation. And we can see between structures that are reported in the inorganic crystal structure database, so experimentally reported experimental reports, you sort of see this monotonic correlation between these other modes, which are associated with the cubic to orthorhombic distortion, which makes sense. Essentially, the larger the radius of the cation, the larger the overall, the smaller the overall distortions are. And so you sort of see a one direction in terms of whether the transition temperature is going up or down. But the interesting thing is these sort of modes I mentioned earlier, this R1 plus breathing mode, which is related to the charge ordering, and this Jan-Teller mode, actually differ between the correlations differ between experimentally reported structures and those computed in the computer using density functional theory. So if you were to talk to your experimental colleague and they were to say, how do I boost the metal insulator transition temperature, you would tell them, in one case, well, you should try to pump this, say, Jan-Teller mode with a laser or some ultra-fast excitation source. And in the other case, you would say, well, actually, no, you should try to, or you would try to inhibit it in this case. In this case, you would say, oh, try to pump it, excite it. So why would just looking at the structural information lead you to this sort of conclusion that's opposite between experimental reports and what's computed computationally? So one important thing to keep in mind when doing any sort of data science study is, well, where did the data come from? Like, what's the sort of context behind how it was created? And one thing to point out is that in density functional theory, the structures are all treated on essentially the same basis. So they relax under the same sort of conditions with similar pseudopotentials. And as a result, you notice this pretty sensible trend that as the arcane radius gets larger, as I mentioned, as the sort of steric packing leads it to be more cubic, all the distortion amplitudes go down, as you would expect. But unfortunately, the experimental amplitudes of these breathing and Jan-Teller modes oscillate sort of dramatically. And that's because even though these refinements are done, are published with pretty good R values, such that, say, the lattice parameters and volumes agree sensibly as you go across the series, the sort of very small local distortions vary depending on the refinement. And as a result, if you were to say plot, say do a linear regression here and plot a line through, it would appear that there's sort of a slight increase because of this outlier for dysprosium. And so actually looking at the structure in a different way besides sort of the rare earth cation radius or the tolerance factor allowed us to point out that there was sort of a gap in the experimental literature in terms of the local structure of this family. And so that made it difficult to just do a simple statistical analysis unless you knew that that was the case. And so it sort of highlights that more, say, structural chemists should maybe consider publishing multiple refinements to potentially indicate the natural variance in the data, sort of the uncertainty in the structures that they're reporting, and that more people should be reproducing these results. So just quick conclusion to this section. So the distortion modes offer a human interpretable featureization of the crystal structure as opposed to, say normal bond lengths or bond angles. The context of the data is very important to be understood when performing some statistical analyses, and visualizing this data points out the need for reproducibility efforts in this particular chemical family, but also likely in many other, say, transition metal oxide structural families. So moving on, metal insulator transitions occur in the nickelates, but they also occur in many other materials. They have a variety of mechanisms responsible for the metal to insulator transition. So I mentioned breathing and Untitled disorders already. And while they are found in nickelates, they're also found in many other transition metal oxide families and in many different types of structures. But there's also these pyrroles-like distortions that can lead to a metal insulator transition that are found in, say, titanates and vanidates. And these have been well studied for a number of decades as well. And there are some materials, say like vanadium dioxide, where the exact origin of the metal insulator transition has still been a matter of debate for decades. And it's not very well understood how you would come up with a universal theory for predicting whether a material is going to have a transition or not. We'd like to find some way of incorporating all of these materials together and come up with a universal scheme for trying to identify yes or no, is this material going to have a metal insulator transition? And so this is where I took a data science approach. So first, just going into some of the background behind other people who have defined what they wouldn't call classifiers, but essentially classification schemes for doing separating metals and insulators. Going back to the early part of the 20th century, Hertzfeld came up with this Hertzfeld criterion of relating the polarizability of the elements to their molar volume, essentially stating that when the molar polarizability became over the molar volume became equal to 1, essentially there was a transition from a metal to a non-metal, and you could see that worked fairly well, given that there was no quantum mechanics involved at all in this sort of classification. And it does predict a few metal insulator transitions in the periodic table in terms of high pressure, say of hydrogen, or volume expansion of mercury, but it was never applied to compounds. And it's sort of even here kind of misses things that are on the borderline. Another effort that was earlier in the 20th century was the Mott criterion. So this relates a critical density of carriers in the material to an effective Bohr radius. Essentially, the argument is that below a certain carrier density, the electrons will fail to screen electron-hole interactions in a material, and eventually they'll become bonded to each other and be unable to move if you imagine the electrons interacting. And this theory actually describes a number of known metal insulator transitions, including, say, a superconductivity transition in yttrium barium copper oxide. But the downside is that getting the critical carrier density often involves doing a number of experiments in the first place, getting a high-quality sample and things of that nature. So it's not very good for prediction. And the same thing, this effective Bohr radius depends on knowing the effective mass of the electrons in the system. So you can maybe get this from doing density functional theory. But overall, it's sort of restrictive in what it can predict. Also, it only uses 2 parameters, whereas we know in modern machine learning schemes, you can get higher predictive accuracy using several features rather than just 2. A related study in 1989, and using the Zun and Swatsky-Allen framework, this is work by Torrance et al. In 1991. I think they originally wrote this in 1989. Uses another 2 parameters, which are derived from chemical intuition. So this this U prime parameter, which is an estimate of the intermetal orbital energy. So these are D states, D metal states on the right-hand side, and oxygen P states on the left-hand side. So they essentially reason that there are 2 ways you can achieve conductivity in a correlated transition metal oxide. You can have electrons excited from an occupied metal orbital to an unoccupied metal orbital, or you can have an excitation from, say, a ligand orbital to an unoccupied metal orbital. So this charge transfer parameter, or this U parameter. And they figured out a way to estimate this using, say, ionization energies and Madelung site potentials, and just structure. It requires the structure of the material, which is kind of a downside. But they were able to achieve relatively good separation of simple oxides and some perovskite oxides at the time using just these 2 parameters, where these black dots are metals, which are typically clustered in the lower left L, and the insulators are typically pushed up to the right. And they drew these lines by hand rather than in any sort of rigorous statistical learning technique, but it worked quite well. And they reasoned that things that were close to this line, which is like titanium 304, were known to have metal insulating transitions. But they were sort of limited by the amount of data that they had and sort of their choice of descriptors. More recently, within the last decade, there have been a number of studies looking at using machine learning to predict insulators or metals under the band theory definition, so whether the material has a 0 band gap or something higher than 0. And these efforts have been really successful, achieving high accuracy scores. I showed one example here from Professor Bergosh's group based on experimental band gaps rather than, say, density functional theory band gaps. But there have been a number of high throughput groups who have done machine learning on band gaps and showed high accuracy scores. Here, this AUC curve here essentially is 1 when you achieve perfect classification with no false positives, so entirely true positives. And they showed that the amount of true positives and true negatives that they were able to predict of metals and non-metals is quite high. The nice thing about the machine learning systems is that they are super fast and very accurate compared to, say, a human trying to do this by hand. And one of the problems with these studies, though, is that they don't focus on the transitions as much. They mainly look at, here, given a simple structure, given a single composition, what's that assignment going to be? Whereas I was kind of interested in, is there any way of identifying materials that are on the cusp or maybe are just have transitioned from a metallic state to an insulating state? Could do that. And so I wanted to do my own machine learning study. To do that, I first had to collect known labels. So in my case, because it's based on metal to insulator transition, I looked at, say, experimental reports of resistivity versus temperature data, because I consider that the most reliable. I understand there are other ways you could think of basing this criterion. But given sort of the known limitations of DFT and predicting some band gaps, I figured it was the safest way to do it. And I primarily focused on transition metal oxides because those are the materials most commonly associated with metal insulator transitions. So unfortunately, my data set is rather small in size because it's culled by hand from experimental reports. But I had a number of metallic oxides, a number of insulating oxides, and to my extent of my knowledge, one of the largest sort of, I guess, metal insulator transition data sets with transition temperatures and resistivity values across the transition. And I put it up on this data hosting website called data.world. And essentially, you can see I use a dimensionality reduction technique here to visualize the data set that I have to show some different chemical families. So while it is predominantly oxides, there are some sulfides as well. But you have things all the way from binary titanates to sort of exotic lanthanide cuprate, copper iron high pressure phases to nickelates, like I mentioned before. Some boring compounds like rock salt structures and perovskites. And I apologize here if you're red-green colorblind, but there's a metal insulator transition class, an insulating class, and a metallic class. I think that's the only plot where I use this color scheme, so hopefully it's not too much of an issue going forward. And of course, to do a machine learning study, you have to have some kind of vector representation of materials to feed into the algorithm to do the statistical learning. So I wanted to use a variety of features from the past studies, in addition to a few extra ones. So one of the most commonly used set of descriptors for talking about materials composition is the MAGPIE feature set from Professor Wolverton's group. Essentially, you take elemental properties that are either computed in DFT or come straight from the periodic table or electron counts, and you average them by the stoichiometry. So if it's, say, barium titanate, you have 3 times as many oxygens, so you weight that more. And this has been found in numerous other machine learning studies, perform pretty well at separating similar and dissimilar materials in terms of properties. I also take some descriptors from the Zanen-Slotsky-Allen framework I mentioned before, so that U prime and delta parameter, I use that those 2 features in my my data set as well as ionization energies, which are used to compute them, the Madelung site potentials, which feature as well. These are more sort of hand-tuned features because they don't necessarily apply universally across the periodic table, but primarily to oxides. And then I also have crystal structural information because the structure is so vital to understanding the metal insulator transition. I have to be able to distinguish between things with dissimilar metal-metal and metal ligand distances, bond angles as well. I have, related to the density, I have the volume per atom of that structure. And some other structural features that don't appear on this list because they would take up too much space, as well as this global instability index, which is based on sort of an average deviation of bond valence. So these R parameters, Rij parameters, are the actual bond lengths, and then R naught are known bond lengths from, say, a crystallographic database. It's essentially an estimate of how much do your bonds deviate from what you would expect given this normal bond found in the inorganic crystal structure database. And I put that all together, it comes out to about a 90-dimensional data set. So it seems pretty high, but hopefully we should be able to separate very complex materials from each other. And I feed this into a gradient-boosted classification algorithm, and I assess it using cross-validation. So really quick, I'll go over what each of my metric plots are. So this is that same plot I showed earlier in the metal insulator separate classifier. You have the true positive rate on your vertical axis here, and your false positive rate on the x-axis. And ideally, you'd like to achieve 100% true positive rate without getting any false positives. So you want these curves to be in the upper left. And each of these curves here is from a different random split of the data being used as the test set, and me training the algorithm on the other, say, 5/6 of the data set. And we can see that while there is some variance, the performance overall is quite respectable, with a mean area under the curve of 0.95. However, this performance could be over-optimistic if the data set is imbalanced. So say there's a lot more materials that don't have metal insulator transitions than do have metal insulator transitions, which is the case in my data set, but even more so would be in a larger data set. And the other reason it might be over-optimistic is if there's a high amount of clustering. Say you're working on superconductivity and you know all about pnictides and BCS theory superconductors, you would very likely have a high predictive accuracy of a machine learning model trained on those within those materials, but say you might not predict the Coop rates to be superconducting because they're so different from the particular clusters of materials you have known. That's very likely the case in this data set as well, because it's known materials are often discovered similar to other materials. So to sort of get around the first problem of if the data set is imbalanced, which in my case it is, you can also look at precision recall instead, which is averaged by the amount of false positives in the data set. So taking into account the distribution of the classes, you would hope that you would have a high precision or high amount of true positives relative to your true positive and false positive count. And you would also hope that you have a very high recall, which is essentially you're picking up as many true positives as possible out of the total amount of things that should be positive. So you want to identify all the metal insulator transitions without guessing everything to be a metal insulator transition. So ideally, these curves would be on the top right, and you can see there's a bit more variance in the precision recall distribution here, and it's likely due to the way the data is split into the highly structured data, highly clustered nature of the data. But it's one thing to do cross-validation, another thing to ask, well, what's the state of the art in this sort of question? And so Haywen, who's in the audience, conducted a survey of 52 PhD students, postdocs, and professors, where he asked, given this materials composition, do you think it is a metal insulator, first of all? And then if it is, say, metallic, do you predict whether it's going to undergo a transition or not? And the result for this classification is that the humans tended to guess that a material would have a transition more often than it actually would, whereas the machine learning system was much more conservative in that regard. But in terms of actually identifying total transitions, because the humans tended to be very gung-ho about guessing yes, they achieved a recall score that's within the same sort of interquartile range. But meanwhile, if you look at sort of the harmonic average of the precision and recall, the machine learning system actually outperforms the humans, the majority of humans. There were a couple of people who displayed better performance than the machine learning system. And you might expect that there's some unfair comparisons because the machine learning system is using 90 variables and humans are using maybe 2 or 3 factors at most typically, plus their memory. So that it could go the other way. The humans might have just memorized, if they were a solid state chemistry professor, they might have just memorized all known MIT materials, and then it might be an unfair comparison. But for the average person, it's quite a difficult challenge. So that's good. But one thing that we'd like to know is the machine learning model actually doing some kind of learning some kind of interesting physics or not, or is it using things that are totally irrelevant to what you would expect a human to want to use to make these predictions? And so this plot is really busy, but I'm going to walk through it really quick. You can use this concept that has come out of the machine learning community for say, diagnosing the interpretability of machine learning models called Shapley importances. There are other feature importance scores, but one of the nice things about Shapley feature importances is that you can look at a particular sample in your data set, so say a particular material, and say, what evidence was it using when it made this decision about whether this material had a transition or not. And you can see here these bars represent different factors or features that went into making the decision, and the size of that bar represents how much evidence one direction or the other it gave. Things that pile up towards the left are usually assigned no predicted transition. The things that are going to the right have a higher probability of being assigned a predicted to have a metal insulator transition. And we can kind of see there are a number of say features from the MAGPIE feature set here based on composition or valence electron counts that are used in this estimation. And as we saw earlier, neodymium indicolate does have a transition, so we're glad. It predicts a much higher probability of it having transition than the baseline, which is good. But one of the interesting things is it's using this max metal-metal distance. And this is something actually from structure. And we would like to know, what's the reasoning behind why it used that feature versus something else. And it turns out a lot of both the composition and the structural feature are related to identifying that it's in the nicolate family primarily. So it's identifying chemical trends or chemical families that have this transition, which works pretty well for diagnosing, but maybe could be counted as, say, overfitting to your training set. So that was one work theory example, but we can look at, for every material in the data set, what factors were used to assign the prediction, and what was the likely distribute, were the features, say, all equally important on average, or were some features massively important in a small subset of cases or not, which is something you don't typically understand from a machine learning model. So looking at just say one row here, this is the particular feature. It's going from top to bottom. It's ranked by the mean absolute SHAP value used here. So on average, this feature was the most important, and then so on and such. Things on the left-hand side, again, will be things that are predicted not to have a transition, and things on the right will be predicted to have a transition. You'll notice right away that there's a lot more strong belief in not having a transition than evidence of transition. So it seems that there are many multiple features that will go into assigning a yes prediction, but there are some features where you can very confidently just say, no, it'll never transition. And the actual color of this feature, so from red to blue, is scaled based on the range, the max and min range of that feature. So things that are blue have, say, very minimum average covalent radius. Things that are high have very high. Things that are red have very high average covalent radius, or deviation in average covalent radius. And a lot of the structures with the highest deviation, for instance, are, say, rare earth oxides. So like lutetium-203, which are known to not have transitions at all, but have very high deviation in their covalent radius. And so you can see the top 10 features here. A lot of these relate to, just say, compositional families or properties in the ground state. But I'll point out that some of the features that have not been traditionally incorporated in, say, software packages that provide features like this max metal-metal distance in the structure, this Madelung site potential of the anion, and this Hubbard U sort of parameter from the ZSA framework are not, so haven't been traditionally used, but they show up as important features, which might indicate that they could potentially be incorporated into, say, machine learning workflows that other people use. It might be predictive of other properties, or just predictive of metal insulator transitions. And you can kind of see some of these features seem pretty interesting in that they sort of scale with the probability of a prediction. So the Madelung site potential, if it's very high, indicates that there's probably not going to be a metal insulator transition. But as slowly as it goes into sort of the middle range, there's sort of the middle probability, and then very low values tend to be a high prediction of transition. This is neat. I think it's a sort of technique in the computer science literature that should be more widely used in machine learning, where we're trying to deal with models that we want to be interpretable and understand if they're overfitting or not. So just to conclude, this machine learning model can predict metal insulator transition temperatures with accuracy of most human scientists, but we can still not have to treat it as a black box because we can use feature importance scores. These 3 features that I mentioned could be useful features for screening, for MIT screening and say larger databases. And as preliminary work, I've downloaded a set of all the oxides from the materials project, and I'm scanning through them now, seeing whether some of the predictions that come out of this model are going to be useful or not. I'm actually doing creating a new version soon with a materials informatics automation tool called AutoMap Miner, where I can incorporate these features in so that other people can use them, and I don't have to hand tune the model, which is nice. Yeah, as I mentioned, I'll be incorporating code into that project so that other people can use this work without having to entirely reproduce my data set and such. So to summarize my talk, I showed how density functional theory can be used for design of functional properties in these hexagonal perovskates, which are underexplored. I then showed how data visualization can highlight the structure property relationships in rare earth nickelates and illustrate discrepancies or missing sort of areas of experimental literature. And then I also showed how machine learning can produce a useful model for predicting metal insulator transitions and potentially teach us something new about how we could devise a universal predictor for metal insulator transitions. So some of the work that I haven't worked on directly, but I'm really excited hearing about people in the materials science community work on are, so going beyond my hand-built experimental data set to use massive scale natural language processing to go through the entire literature and actually build databases automatically with many thousands of compounds rather than a few hundred. I think that is a huge potential impact for materials discovery. I also think using feature importance scores that are developed as well, but also say influence function scores. So actually identifying not just which features are important in a model prediction, but identifying which materials are most crucial to the functioning of a machine learning system. Some of those results are very promising. And then in terms of, you might notice a lot of these have to deal with like expanding the data set robotics. So increased automation of graduate student labor, more materials faster, something I'm really excited about. Finally being able to test all of the predictions in high throughput, iterate automatically. That's something that's coming online that I'm very excited about. And then in terms of actual material description, one thing that I think we can learn about from chemistry is the use of generative models like generative adversarial networks and variational autoencoders for devising new representations of materials based on, say, large structural data sets or other such things. I've seen many examples of this being applied to drug discovery, and I think material science community will start realizing in the upcoming years how useful these sort of latent representations we learn from generative models are for materials discovery and generation. With that, I'd like to acknowledge the people here. So the people who directly contributed to this work in the group. So Pei Wen, thank you. Unfortunately, he's not here, but Dr. Daniela Pugioni, Dr. Michael Waters, thank you. My advisor, of course, James, thank you so much. My committee and my qualifying committee as well, who gave me a lot of valuable feedback early in my grad school career. I'd also like to thank my fellow members of the Materials Theory and Design group. Without you guys, I never would have made it here. An undergraduate advisor, Professor Candice Chan, who convinced me that research was something that I can consider doing back when I was fresh out of English literature and didn't know any science. As James mentioned, my summer research mentors, so Dr. Tarab Bookman, Dr. Lisan Yang, and Patrick Riley, the last two from Google, and Tarab from Los Alamos, taught me a lot of valuable skills and gave me a broad sort of introduction to the materials informatics community. And of course, my friends and family, if it wasn't for my wife, Gentry, and my parents, I wouldn't be who I am today. And last but not least, I'd like to thank the funders of the work, the Department of Energy under the UltraFast program, the NSF under the DEMREF program, and the Compute Resources who allowed me to do the density functional theory. Thank you.
So we'll take questions now from the audience before the close of the session. I have a question. Richard looks like he wants to ask something.
I was speechless.
I didn't
have a question.
No.
Well, can I ask a silly question?
Oh, sure. Yeah. Yeah, please.
Does Patrick Riley really not have a PhD? That seems impossible.
I don't believe he does. He's a software engineering by trade. He worked in search for a decade, and then he got tired and wanted to do something beneficial to humanity, so he started a science group. As far as I know, no one ever called him doctor in my presence. So.
All right, so if there are no questions from the audience, we'll go to the closed door session. So we'll ask everyone except the committee members to leave.
I'll make sure not the live stream. Thank you, everyone. Oh, wait, I gotta end this stream.
Who watching?
Oh, I didn't check to see how many people.
Did you record the recording?